Welcome to part 3 of fractal market analysis. Last time we kind of went over some basic properties of fractals, and I'm just going to continue that. We left off with self-similarity, and so now we're just going to describe why self-similar objects are described by power laws, and obviously all fractals are self-similar in some way, and so fractals are described by power laws. I mentioned in the previous video at the end about a paper that has a lot of, a paper that describes similar things, going over how power laws relate to self-similarity in fractals, but it has a lot of explanations that really resonate with the reason that I think we all like fractals. And so I'll just start off with another quote from that paper. With power laws, it's possible to express self-similarity of the large and small, i.e. to unite different sizes and lengths. In fractals, for example, there are many more small structures than large ones. Their respective numbers are represented by a power law distribution. A common power law for all sizes demonstrates the internal self-consistency of the fractal and its unity across all boundaries. The power law distributions result from a commonality of laws and processes at all scales. So this is just saying, again, when you zoom in on a fractal, you see another copy of itself. It might not be an exact copy. It could be, rotated in some way, but the proportions of it remain the same as you zoom in. So fractals scale according to power laws because self-similar objects are described by power laws. Not all self-similar objects are fractals, obviously. So a power law is a relationship between quantities wherein a relative change in one quantity results in a proportional relative change in the other, independent of the initial size of those quantities. So for example, the area of a square in terms of the lengths of its sides. So we get the area of a square, which is a two-dimensional object, and when we relate this back to fractal dimension, we can see the dimension is right here. We know a square is a two-dimensional object, and a equals n by n, which equals n squared. That's the power law relationship right there, which is described by this exponent 2. If we double the length, the area increases by a factor of 4. So in this case, we're scaling it. We're making it larger. We're scaling it larger. So now a equals 2n times 2n, which is 4n squared. The proportional increase in a is determined by the square of n, regardless of the size of n. So this is regardless of the initial size of the sides of the square. It's based on the relationship. So this is essentially what the power law is. A relative change in one quantity results in a proportional relative change in the other, independent of the initial size of those quantities. So this is the power law relationship between A and N. Power laws are scale invariant. So you scale any power law relationship by a constant, only multiplies the original relation by another constant. So we're going to define, I should have defined this first, but we're going to define a function, f of x equals ax to the negative k. So in this case, a is a constant, x is our variable, and negative k, the k is a constant. So if we then scale the variable, our variable x, whatever we want to make that quantity, if we scale it by another constant, it simply equals that relationship. So f of x equals ax to the negative k. So that's what this f of x here represents. It's scaled, it's multiplied by this constant raised to another constant, c to the negative k. So overall, this is just going to be a constant multiplying our f of x. So the function is proportionately scaled. So this is essentially, this is how I would best understand this power law relationship, is because you can see, if you zoom in, it multiplies everything in that function by another constant. So everything is proportional to itself, or proportional to what it originally was. Each power law relation with a particular scaling exponent negative k is equivalent to others with the same exponent up to constant factors. So this means, let's say you have f of x equals x squared. That is equivalent to 2x squared up to constant factors. The constant factor would be 2. So literally this is just saying the same thing, just in a different way. It's saying that, if you have the same exponent, the same negative k, everything described by that relationship is going to be the same, only multiplied by a constant. So this exactly describes the behavior of self-similar objects when we zoom into them at different scales. Because when we zoom into them, we're just kind of magnifying all of the quantities, and they all magnify with the same proportion. This is where the idea of fractal dimension comes from. So I mentioned that before again. So we know in Euclidean geometry that a square has dimension 2, and we see that with its power law relationship here, with its area and the lengths of its sides. A good example of power law relationships and just fractals in general in nature is lungs. So in the book that this entire series is based off of, he does mention at one point that you can kind of think of the human body as a fractal. And so not necessarily like the shape of my body, but just things within your body have this kind of fractal nature. And the more you zoom into them, the finer detail they get. Like, you can zoom in with your eyes and you see that fine detail, and then you can zoom in with a microscope, and so on and so on and so on. And it just seems there's infinite detail the further you go in, and a lot of the structures within our body are self-similar. And one of those is lungs, and lungs have this kind of chaotic property too, that I was mentioning in the previous video, where you can say chaos is local randomness but global determinism. So we're gonna talk about this in terms of how lungs branch, because that's really kind of like the characteristic feature of lungs, is that they have all these branches. So we start with the trachea, and then it splits off into 2, and then each of those sides splits again and again and again. And so we want to understand, what kind of mathematical relationship describes how lungs are going to branch, because we know the trachea is bigger than the 2 branches that come off of the trachea, and then those 2 branches are each bigger than the branches that come off of them. So things seem to be getting smaller and smaller. So yeah, the branching mechanism of lungs has been extensively modeled within each generation. So a generation we're just going to describe as like a branching. So our trachea is like our initial starting point, it's our seed, and then the 2 branches that come off of it, that's the first generation, and then you have like the second generation, so on and so on. Within each generation, the actual diameters have a range. Some are larger and some are smaller than average. So we know that within each generation there is an average size for the diameter of those branches, but there is a range, and the range is kind of random. Like, the range likely follows a normal distribution, but they all form this average. And so with that, you can see that local randomness. There's kind of this random factor that decides what the diameter of the branches are going to be. It's the size is random, even though it follows this like global average. An exponential scaling law fits only the first 10 branching generations. So there is a paper from the 30s, I believe, where they attempt to describe the branching law of lungs with an exponential scaling law. So a power law is, x raised to a constant exponent, whereas an exponential law is a constant raised to a variable. So like that would be like 2 to the x or something, rather than x squared. But this kind of scaling law only fits the first 10 branching generations, after which there's a systematic deviation and the generations follow power law scaling, which has better error tolerance. So there's 2 things with this. The first is that in the previous video, I mentioned that fractals are typically self-similar for a discrete set of values. So if you have an equation or relationship with a parameter, at certain values of that parameter, you will see self-similarity, but at certain other values, you won't. And so this kind of shows what is meant by that. For the first 10 generations, the generation number, I guess, being the parameter, you can describe it by an exponential law. But then after that, it follows a power law, and power laws describe self-similar objects. So only for a discrete set of values are lungs self-similar. And again, this is important when we're going to talk about markets and fractal time series, and when we discuss stocks and bonds versus foreign exchange, we'll kind of see how this works there. And then the second thing in this statement is that power laws have better error tolerance. So if you change the value of x, for example, if you have a branch that's much smaller than the average value, or much larger, you would consider it to be kind of an error. You don't want branches that are much smaller or much larger than the average. And so since the next generation from that error branch is based off of a power law with that branch, the error does propagate. So everything that comes from it will have that kind of like slight error. But the error tolerance comes from the fact that if you have that x, if your x value is much smaller or much larger than all of the other x values, the error doesn't grow as fast because the exponent is constant. So as opposed to an exponential scaling law, where if you have, for example, 2 to the 3 versus 2 to the 4, like it just grows much faster. And so this is what makes nature so robust, is these power law relationships. And it's why when we look at natural objects, we can think of them as fractals, and they're kind of like more roughly defined fractals. They're not really perfect. They're not really the stuff that you see generated by computers, but they do have these fractal properties, and they have that property where you zoom in and you see finer and finer detail. We still don't know what the smallest thing in the universe is, It could just go on forever. There could just be, there might not be a smallest thing. This is the thing that I was mentioning just right at the beginning of the slide, is that lungs show self-similarity for a discrete set of values, because for the first 10, you can describe the branching mechanism by an exponential scaling law, but after that, it's described best by a power law. So now to give a clearer picture of what a fractal actually is, using an example, we'll look at the Sierpinski triangle again, because I think it's really easy to see its fractal structure. So basically what's happening here is that with each generation, and there's a few different methods for constructing a Sierpinski triangle, but it is that iterated process. And like I mentioned previously on the self-similarity slides, which was in the previous video, iterative fractals that are described by iterative functions are often exactly self-similar. So we start with this big filled black triangle, and then 3 copies of itself are made, and so now we have this kind of like Triforce type of thing. But then 3 copies of this are made, so you have one here, and here, and here, and then this whole thing, 3 copies of it are made again. And you just keep going and going and going and going. And so, like I mentioned in the previous video, this right here is not the Sierpinski triangle. This is just a representation of the Sierpinski triangle, because the Sierpinski triangle is the limit. So you need to do this again and 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 again, an infinite amount of times. And that that infinite kind of process right there. That's what the Sierpinski triangle is. So this is just what it looks like at this level when you don't, because you want to create, yeah, again, 3 more copies and then stack them in this way to create this again. So we did one construction of the Sierpinski triangle just now, where you basically are just creating 3 copies of itself and stacking it on top. And then we also saw how you can construct it with the chaos game, which works if you run the chaos game an infinite amount of times. That will create the Sierpinski triangle. But then you can also do it this way. You find the midpoints of the line sequence of the largest triangle, and then you connect the midpoints, and then you iterate it over and over again. So all of these methods of constructions for the Sierpinski triangle are iterative methods. So find the midpoints of the line segments of the largest triangle. So that would be here, 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 and then you connect them, and then you can see how that kind of cuts this out. And now this part is the largest triangle. So these are all equal size, so you do it again. You find the midpoints and you connect them, and you get this. Same thing. Right, so like I said, the Sierpinski triangle also has exact self-similarity. The attractor for the system described by the chaos game is the Sierpinski triangle. And if you don't know what I'm talking about, watch part 2. The part 2 explains it. So we're essentially constructing 3 copies of the triangle in its present state each time. And this is, I'm now going to kind of tie this back into fractal dimension before we actually go over fractal dimension in more detail. The Sierpinski triangle, this idea that you're essentially constructing 3 copies of the triangle in its present state each time you iterate the process, will kind of illustrate how the fractal dimension works. So for an integer number of dimensions d in Euclidean space, when doubling a side of an object, 2 to the d copies of it are created. And this is exactly what I was mentioning when we were talking about power laws, with the relationship between the area of a square and the length of its sides. So, for example, 2 copies for 1D objects, because it's 2 to the 1, like a point. 4 copies for 2D objects, like a line or a square. Remember, when we doubled the sides of the square, we increased the area by a factor of 4, and 8 copies for 3D objects, and so on and so on. For the Sierpinski triangle, doubling its side creates 3 copies of itself. So now we have 2 to the d equals 3, and so this d here, that's our fractal dimension. So now we solve it using logarithms. Log base 2 of 3 is 1.585. So the Sierpinski triangle has fractal dimension 1.585. Now we'll actually talk about fractal dimension. So what this is called the Koch curve. I'm not really sure if I'm pronouncing that correctly. If you connect this little section here and you put it down here, you get something called the Koch snowflake, which is also a fractal. But again, this is an iterative process, and this is not the fractal. This is just a representation. You would keep doing this to infinity. So previously we said that fractals scale according to a power law, y equals ax to the b, where b is not necessarily an integer, and it's called the fractal dimension. So fractals have a non-integer fractal dimension. The fractal dimension is a ratio providing a statistical index of complexity, comparing how detail in a fractal pattern changes with the scale at which it is measured. So it's a measure of the roughness, and I mentioned this in the part 2 as well, how the roughness of fractals is the reason that they're non-differentiable, and that when you zoom into them, you get more and more and more detail. So we will go over more of an understanding of what complexity is, but it's basically, but this is what the fractal dimension is describing. It's how much of a fractal it is. It's a statistical index of complexity, comparing how detail in a fractal pattern changes with the scale at which it is measured. So we've gone over most of this already. The fractal scaling properties of an object are quantified using fractal dimensions. You can also say that the fractal dimension is a measure of the space-filling capacity of a fractal pattern. And there's an example here, but space filling is a mapping of a one-dimensional line into two-dimensional space. It's a continuous curve that will pass through every single point in a given space. So remember in part 2, I was talking about how a random walk has a fractal dimension of 1.50 because there's a 50-50 chance that it's going to move up or down between one dimension and two dimensions. So it's very rough. And so it's not a line, but it's not a plane either. So it's exactly in between 1 and 2 dimensions. That's what a random walk is. And you could see that even with the picture of the random walk on the random walk slide from part 2. So an example of this is the piano curve. So the piano curve is a one-dimensional object being mapped onto two-dimensional space. It's a space-filling curve. It fills every single point of two-dimensional space, even though it's a line. This is what it looks like. So again, it's an iterated thing. And this is as far as it will go here. But again, this is just a representation of the piano curve. You're going to take it to its limit, and then you can say that this line fills 2D space. And when we say it fills 2D space, it hits every single point in two-dimensional space, which is pretty crazy to think about. But you can see how if you continue this process to infinity, how it would. So these two statements here are pretty much saying the same thing. We're talking about fractal dimension being a measure of roughness. So how far do you zoom in? And it gets more complex the more you zoom in. And that kind of already gives you a sense that it's filling up space, because you keep zooming and there's just more detail. There's more and more and more detail. So you can kind of see how you could define a fractal that seems like it should be a line, but it fills so much space that it's almost two-dimensional. Or you could have one that's two-dimensional, but it's almost like it's between 2 and 3 dimensions, like a wiffle ball. So it's a measure of scale. So for example, a trivially self-similar cube of side length L can be decomposed into n to the 3 facsimiles of side length L over n with corresponding scaling ratio R of n equals n to the negative 1 over 3. I have an image of this, actually. So this is what I mean. So a cube is trivially self-similar, and what that means is just there's nothing much to say about it. It just is trivially self-similar. It's trivially true. I'm not sure how to describe that. I'm so sorry. So here we're going to decompose the cube into 8 versions of itself. So these are exactly, like these 8 copies of the cube are exactly the same as the larger cube. And so when our n is equal to 2, we decompose it into n to the 3 facsimiles of itself. So 2 to the 3 is 8. When our side length is L. When our initial side length is L. And so now each of these facsimiles has side length L over n. So L over 2. I hope that makes sense. And then to generalize that, we can see, so we define our scaling ratio as this n to the negative 1 over 3. So then to generalize that, we see that the scaling ratio is actually n to the negative 1 over the dimension. And then if you solve for that using logarithms again, you get d equals negative log of n, that's the side length, over log of the scaling ratio. And this works for exact self-similarity. And there's other ways to figure out the fractal dimension, including box counting and other methods. So this is box counting, and basically you're just kind of, again, you're kind of estimating the space fillingness, the roughness of the fractal by kind of overlaying it with boxes at different scales. And I won't go over how to do this in too much detail because we don't really use this for fractal market analysis, because fractal time series, which is how we're going to model markets, we're going to say that markets are fractal time series. Those are fractals in time, not in space. So when we use spatial methods to measure things that don't exist in space, you can't really do it. So box counting isn't relevant to fractal market analysis, but it's just another way to kind of explain fractal dimension, just in case it's not clicking with the other ways that I described it. So the number of boxes is a function of the box size, and the box size is kind of a proxy for the scale that we're looking at this fractal on, if that makes sense. So with a bigger box size, we're looking at the fractal from, a wider perspective, and the smaller the box size, the more we're zooming in. So the number of boxes that it actually takes to cover the fractal is a function of the box size. And so S and N here, where S is the box size and N is the number of boxes, have a power law relationship because it is a fractal and it scales according to a power law. And this is just the way that power laws work. If you have two things that are related to each other by a power law, if you take the log of both and plot it, you'll get a linear relationship. So this is what it is here. And this is a negative slope, but with this box counting method on this Koch curve, we see that the fractal dimension is roughly 1.28. We'll just ignore the negative there. We can just do 1 over n here, and it'll have a positive slope, so that doesn't matter. So this is your standard y equals mx plus b formula, it's like a tangent line formula. You've probably seen it in calculus. It's just another way to calculate fractal dimension, and you can do this process over and over and over again and make smaller box sizes, and you'll get a more accurate reading depending on how detailed your object is to begin with, because obviously fractals, as I've mentioned before, you're taking the limit, so you're doing that iterated process to generate that fractal over and over and over again into infinity. So the box counting method is only going to be as effective as the detailed representation of the fractal, because you're never going to have the exact fractal. It's only as good as the representation of the fractal that you have. I'm going to stop the video here. It's getting quite long. In part 4, we'll start the example of the logistic map, finally, and then we'll go on to explain chaos, and then finally we'll end with actually describing what statistical self-similarity is, and what a fractal time series is, which is going to then launch us into the point where we can start understanding how we're going to analyze markets. So I'll see you in part 4.